So my name is Santiago. Like George said, I'm a researcher here at Caltech. Been collaborating with astrophysicists, geophysicists, biologists, fluid mechanics people for the last 20 plus years. I'm also faculty at Art Center College of Design, where I teach interaction design, mostly focused around data visualization. So for the next 40 minutes, I'm going to give you a quick overview of just some very basic stuff when it comes to visualization. I'm not going to go into much depth about any one topic, and I'm going to jump over different areas quite a bit. But hopefully you get a nice overview of some strategies that make visualization more efficient. And that all starts by understanding what do we mean by data visualization. So what we usually mean by data visualization is just having some data and putting it in a more understandable format, something that we can actually try to start understanding. So that would seem to be visual, but that's not necessarily. It could actually be haptic feedback. It could actually be sound. It could actually be a whole immersive experience. It could be an art installation where you actually get some emotional feedback that lets you understand the data. That all is covered under data visualization. And if you look for papers and research, you'll notice that there's quite a bit of variety of what's out there. But it all starts with understanding, okay, let's go back to the visual. What is our visual system good at doing? So our visual system is good at understanding patterns and coming up with patterns, right? So how many people here can actually see the snake in there? Okay, so most of you can actually see the snake in there. So our system, our cognitive system is made to find these patterns and try to interpolate the information from it and try to understand things from it. Of course, if you see a different image, you might actually start seeing other things. Like most people see the face on the tree there. So our system, our cognitive system tends to overfit, right? It tries to find things. So that means that when you're doing data visualization, especially if you're doing visual stuff, you know, our body wants to keep us alive in the wild. So it's okay to see snakes even if there's no snakes, as long as we actually see the snakes when it's necessary. So the same way, if you're looking at data and you're looking at an ocean of visual points, you might be seeing clusters, but there's always a chance that what you're seeing is just you're over-interpolating what you're looking at. So, okay, let's snap back to reality a little more. What is data visualization? So data visualization is this large pipeline of work. And when you look at all the work that's been done in data visualization, it actually goes all the way from data acquisition, parsing the data, filtering, mining, finding representations, refining it, and eventually interacting with it. So visualization, publications in data visualization, people working actively in data visualization, actually try to encompass a lot of this work. In the tools that you'll see out there for particular data visualization, we'll do data mining. We'll try to do some interesting representations. We'll have GUI interfaces to let you select, to brush, to highlight things. So it's very much a multidisciplinary thing. And you know, there's a quote by Colin Ware that we don't know much about our cognitive system. So basically, visualization people are just good artisans. We know how to put things together. We know how to tailor things. And that's what I like to think of myself, just an artisan who's seen a little bit about many things. So let's start at the beginning, one more time. How do we represent data? So we represent data through encoding channels. We have ways to translate numbers or variables into visual representations. So the most basic one is position. And our cognitive system is actually very good about perceiving position and differences in position, especially in 2D, especially on a screen. Now, this changes a little bit if you're actually doing VR, because you don't have the reference point of the framework of the actual screen. But for the most part, we're pretty good about telling if the differences in position. So right there, we have two channels. If we do 3D, we actually have three channels we can actually encode data, translate data directly into. We can encode data as scale. We can create a visual entity and we can scale it depending on a variable. If it has a particular shape, we can actually orient it. We can do rotation. Then we can use color. And I'll have a whole little section about color. But the punchline is that we don't use RGB. We try to use just luminosity and hue. Those are what you want to stick with. So we have two channels of color which are very easily perceivable. One is the luminosity, how bright it is, and the other one is just the hue, what tone of color it is. Then you can get into a little more complex things, like shape, actually mapping different data, especially if it's categorical data. We can actually map it into different shapes. We can actually create shapes depending on variables as well, and we'll talk a little bit about glyph generation a little later in the talk. The other thing you can map is motion. So you can actually have things that kind of vibrate or move around depending on a data variable. That channel is extremely good at encoding data. That actually stands out again, our cognitive system is made to kind of pick out things that are kind of moving because we want to stay away from tigers in the bushes. We can do extra things that we actually do markings. We can actually put little hatch marks. We can use textures. Enclosure, actually having a bunch of points and putting a line around them. Our cognitive system is good at understanding what do you mean and creating hierarchies out of that. And every time we start talking about these things, now we're actually using lines. So the line length and the line width that we use itself, it is all another channel. So there's easily between 16 and 20 data channels we can encode. And the question is always, well, can we use all those channels? And the first answer is well, first of all, there's an order to how precise we can be at each of those channels. In general, through HCI studies, people have said, okay, let's see the error if we actually try to measure things in different positions on the screen, or different lengths or different slopes. And position, where our cognitive system is pretty good about determining position. And this is 2D, so we have the framework of pixels and actually the reference point of the screen itself. In VR, it would be different. We have line length. We have once we're talking about rotation, we're pretty good at telling when things have slightly different rotation. Now shape and area, we start getting in trouble, right? Especially area, because a circle, does it represent the diameter or does it represent the weight of the shape itself? It depends a little bit on how we're looking at it. Volumes we're extremely bad at doing, and actually color, especially when it comes to pure to small changes in color, our system is actually pretty bad at it. But that said, it actually depends on the type of data that you're using. For instance, if we're talking full quantitative data, just decimals, then position and length are pretty decent ways to encode decimal data. But if we're talking about ordinal or categorical data, nominal data, when you have very specific categories, then things like hue all of a sudden are pretty good. In other words, if you have 4 different categories, if you assign 4 completely different hues, and you do put those on the screen, our system is pretty good at telling those. But if you have a continuous value, and you just start touching different shades of red and shades of green and shades of thing, then our system is pretty bad. So for quantitative data, hue is pretty down the list, but when we're talking about nominal data, hue is a little higher on the list. Okay, so now we understand that there's all these encoding channels. We understand that we have to be careful how to use them to encode. They're going to have qualities that make some better and some worse. Okay, so how do we plop them on the screen? What kind of plots can we do? So there's this a business professor of all people that came up with this little chart of just different plots. At the face value, this is not a very good place to start. To just say, yes, if you have multivariable data and it has time changing, you definitely need to use a line chart. Or if you have categories, you definitely use the pie chart. But once we start digging into complex examples of data visualization, everything we look at will come down to some of these basic graphs. The ones that we're most used to are scatter plots and bubble charts. And even complex visualization, like this one right here, is nothing but just a fancy bubble plot, right? So what are we looking right here? So this is actually some work that I did many years ago. We were actually running parallel software on some of the large machines in the national labs, and we just wanted to see how efficient our software was. How much usage do we have? How many CPUs we're using? So we tried to use these visual representations. So if we zoom in, we see a couple of jobs running here. We can see the teraflops. We can see the efficiency. 10% peak of efficiency for running software is actually pretty decent. So anything that's pretty close to 7, you see the outer bubble kind of matches the inner bubble versus things that are low inefficient like 1.2 at the bottom. The inner bubble doesn't match the bottom bubble as much. So how do you build something like this? Well, you start from something very simple, right? You start from a scatter plot. Again, positions really good at matching something. So the data that you see right here, you almost see a pattern, right? You almost see just kind of movement moving upwards. So your data representation, how you choose to visualize it, is going to really start telling a story. And that, in the art world, we love and calling a narrative, right? Your data, the way you present it, most likely is going to have a narrative. So controlling the narrative, controlling what you're trying to put forward to your end user is quite important. So let's go one step further. Let's build up from the information. So we have just basic position. Well, let's start using shape. So in this case, let's start from some circles, and then let's augment it by size by CPU usage. So now we've started from a very simple Cartesian plot to these bubbles. And all of a sudden, the narrative of movement towards the upper right gets completely gone. And all of a sudden, we really just see the massive bubble at the top, and then we see this itty-bitty bubble at the bottom. So that now we start talking about how our cognitive system actually understands these things. Graphic designers love this technique of just kind of squinting your eye. So if you start squinting your eyes, then all of a sudden you just see everything blurry, and there's things that are going to pop out. The thing that pops out first is your first order read. And that's really what you're pushing forward to your user. So when you start mapping variables into the screen, obviously depending on your data, that's going to create the visual representation, which is going to give you different read orders. So really, we're talking about the data is going to change what your outermost visual is going to be. So there is no rules we can set that will say, yes, this mapping is definitely going to let you see these outliers or these clusters, because it's really going to depend on how it finally ends up on the screen. So from here, we can start building up color, and all of a sudden, rather than seeing the big bubble on the top, maybe you actually see kind of a cluster of these warm colors on the right. Maybe you see a little cluster of these purples on the right side. And then we just kind of start layering information, and then we layer number of CPUs, numbers. So all of this is just building up to layers and layers and layers and layers. And that is the magic that when you hire somebody who calls himself a professional data visualization person would know, is just how to apply layers. You start from the basic scatter plots that we talked about, of the line charts or the pie charts, and we just layer information. And the most amazing things that have been created in data visualization is simply by layering information. Now, layer could mean a couple of things. Layer could mean actually putting one thing on top of each other, top of the screen, middle of the screen, bottom of the screen, or actually layering one on top of each other as far as depth. It's almost like layers in Photoshop, if you can think about it. So again, so we go back to the story of the narrative. For instance, here we start with some data, just a little scatter plot. So we have some points. You might see a pattern here. But if we have exact same data, just by choosing a different representation, now we're talking about a different narrative, right? So whereas before this was just points, here now we're talking about a continuity, something that rises and then takes a dip. Now opposite to something like this, where you're actually using white bars to actually exemplify exactly the same data values. So now you have, if you squint your eyes, you see the big blob of white in the middle, right? So you are giving importance to that value, to the weight of that particular element. So that's where design is trying to tell us that what you represent and how you represent it is telling a different story to different users. And then if you actually bring all these things together, you can actually layer this information and actually create something quite more complex. So this is layering of information on top of each other versus actually layering something like a grid. So this is something that, there's a great statistician out of Princeton, his name is Edward Tufte, that kind of curated all this information. And this is one of the things that he found, and he called it small multiples. It's basically a table of information, and by creating a grid of information, then you basically create almost like a movie, right? If you move your eyes from left to right, you see kind of the passage of time. If you go top to bottom, you kind of see changing of different elements at the LA Bay out of Long Beach, all those ships and how all the gases that they release. So you start telling a story, and basically, what was this again? Well, was this nothing but a simple, table plot with a couple of scatter lines and maybe connected as a surface. Another famous data visualization is the Florence Nightingale Rose. She actually did this thing to prove to the Queen how many people were actually dying out in the Crimean War, and most of them were actually not dying in the battlefront, which is kind of the black blob, but they were actually coming home to die in the hospitals in England. So this was her way of convincing people, look, this is our information, it's dynamic, and this is exactly what's happening. People are coming back from the war and dying in our hospitals. And this is nothing but a simple circular plot combination with a line chart, and then the information just layered on top. And the one visualization that Edward Tufte is most well known for is for bringing this one to the forefront, which is the invasion of Napoleon to Russia. So on the left, we have the number of troops that started in France, and they're advancing towards Russia on the right. We have connection to the actual temperature. So you see that at some point, some of the troops split off, and as they keep on going, they have to pass through rivers. The temperatures drop, and they just get depleted, until they finally get to Moscow. They get defeated, and they turn right back around. And every time the weathers get colder and colder, so every time they have to cross a river or something, or some big temperature drop, then eventually, they keep on losing troops. So what's amazing about this thing? Well, again, this is nothing but a simple line chart, but we are layering information, we're layering thicknesses, we're connecting to information. We're actually layering the connection to temperature. We're easily mapping about 8 variables between geography, between temperatures, number of troops, direction, time. So we're actually adding all this information just to create a richer information and representation. So that is how you actually create rich, complex data representations as a whole. We can take a little more atomistic level and saying each individual point that we draw, how are we going to make that a better representation? So that's where we talk atomic visualization. How do you make something better out of a little, little atom? So for instance, let's say we have a number. A number by itself is not very meaningful unless you actually know what you're talking about. So we can create just a small visual element that says glucose, here a value. Now, obviously, we don't know the history of it. So just by adding a little plot of what's happened before that actually gives you context of what that 6.6 actually means. If you emphasize what you're looking at, you actually have a better sense of where you're going. You can actually say, okay, this is kind of the minimum that it should be. This is kind of the normal range. So now, by creating this small representation that you could use to represent many records, you create something that's quite valuable and informative in a very small form. This is what Stephen Few and lots of people call dashboards, is the ability to have these small graphs that pack a lot of information. Now, dashboards in of itself are not easy to read. And usually I do a couple of classes in my data viz class all about cognitive levels of understanding. We can design for things to be reflexive and understandable right away, to be experiential, to be learned. So there's different levels we can design things on. But just to say that dashboards is one of those things that take a little bit of visual learning from your user, but will be quite useful once you actually kind of get the understanding of what each of these bits of information actually mean. So going back to the campaign monitor that I showed you before, here, for instance, the atomic element that we're showing is each individual run, each individual blob. So the same way we created these blobs, we can actually create something a little more complex, like a star plot. Each star plot by itself could actually be several variables. In this case, we're actually mapping 5 variables. We're normalizing the data values, and we're actually making a star out of it. So we can actually layer star plots on top of each other, and this gives you a sense of how all the data compares to each other. Or we can actually use the star plots as individual representations in a scatter plot. And this is what we would call a glyph. So here, understanding the pattern of the glyphs, well, you definitely can see that the higher you go, the things get a little skinnier. So if you start understanding what glyphs actually mean, you actually kind of start getting used to and understanding, you can actually get a sense of what the data is. But it's not the easiest thing to use. Young kids nowadays have been really well trained with this. Most Xbox games like FIFA, every soccer player comes with a little plot that says the defense, the attack. So people actually my son can tell right away from the little glyph who's the best defenseman, who's the best attacker. So there is ways to train people. But you can always exaggerate this. There's this paper that came out in 1973 that said, you know what? Human beings, we're really good at detecting faces. How about you just cram information into a face? We can use, eyebrows, nose size, the eccentricity of your face, and people went nuts over Chernoff faces. There was a gazillion papers published right after 1973 all about Chernoff faces until like 4 years later when people find out, yeah, these are junk. It's impossible to tell information from this kind of thing. To actually go in there and actually try to detect special things, can you tell all the cow faces or all the alien-looking guys? It's quite difficult. It's not easy. And that's because we are creating very visually complex objects and we're tapping into the wrong part of our understanding of even where faces are. So we're not even doing a direct information. There's been very few examples of Chernoff faces actually being even remotely helpful. This one actually might be racist, so don't look too much into it. But it gets some information across. People have been using it. This was something about the medical system and different parties in England. So people try. It's hard. I always think that maybe if you recast the things, actually made it more realistic, maybe they could go somewhere. But for the most part, no, they're difficult to understand. So, okay, so we've been talking about how to represent data, how to look at the data. But when would we ever use this, or how would we use this, or how do we know when to apply all this knowledge? So taking a different look at it, especially from the world that I come with, it's all about the depth of how much visualization you want to do. There's usually the first step where you get your data, somebody gives you data, and you want to do quick inspection. And that usually means you just use whatever tool you have at your disposal. You'll try to use the better tools that actually help you create cleaner visuals, but you'll just use whatever you have at your disposal. Then you usually go through a layer of analysis tools that actually let you actually create prototypes, let you find ways of representing the data that let you kind of click on something or brush on something to actually get information back. And there's a bunch of tools and a bunch of APIs that let you create some pretty strong analysis tools in a very short time frame. And there's finally batch decimation tools. Actually create something that can actually run as your data is coming in, or something that can create a portal. I've seen a lot of changes in the last 20 years. Probably the biggest one is that more and more people are turning to Node.js and to JavaScript and to browser-based technologies, which means that the same things that can actually be done for quick prototyping of analysis tools are the same things that let you actually create something that can actually be a running portal or web server. So there's a lot of technologies that are happening between the analysis tool and batch decimation, which I'll cover. When we look at the whole world of data visualization tools from a different angle. One of the ways to look at the data visualization tools is by what do they accomplish along the different process of data visualization. And for that, we need to go a little closer to the types of data that we're doing. And the types of data really can be separated by the geometry of the data. There's the stuff that are just basically multidimensional records, which AstroInformatics is rich on. And then there's the stuff that that usually has a shape, a dendrite, a tumor in a lung, or fluid across a wing. Things that actually have some physicality to it. These are both fields. One is usually called InfoVis. The other is called SciVis. The data actually, while it looks like different type of data, you can always grab your data and represent it as points in space and triangulate it. So you could actually make it into physical two-dimensional, three-dimensional physical data. Or the other way around, you can always grab physical data and look at all the vertex information and treat it as a table and apply any of the abstract data or InfoVis tools. For the most part, there was the IEEE Vis conference, which has the InfoVis as well as the SciVis sides. There's lots of really cool papers out there. And SIGGRAPH every now and then actually has a couple of interesting Viz papers as well. So now that we understand that, let's look about the visualization process, and let's talk about the different tools that are out there. So first of all, there's the processing algorithms. Anything that lets you kind of manipulate the data and kind of try to understand the data and try to extract things out of the data. So we'll be talking about R quite a bit already, so all you guys are familiar with R. And that really applies to the InfoVis side. For the other side, there's this toolkit called VTK. VTK had exactly the same origins as R. It was an academic tool. 20 years ago, somebody said, I want to build a strong object-oriented piece of code that it's going to be easy for us to teach our students. It doesn't have to run fast. We just has to be flexible, and we can grow it. And as processors got faster and compilation got better, the same toolkit just became the standard tool for data visualization. So VTK is extremely strong. It's C++ based. It has all sorts of front interfaces. Same as R, you have ability to open windows and plot stuff. But at the core, it's just algorithms to actually manipulate data. So a lot of R and VTK works under data visualization. We have then geometry generation, which I'll talk a little later, and then eventually comes to rendering. Once you actually create something that you want to show on the screen, then it comes up to actually creating those into actual pixels. For the most part, we're going to use the hardware that we have in our machines. Most of our machines have OpenGL graphics cards that will actually look at the points or triangles and actually make them into actual pixels going on and off with different colors and different shading languages. For the most part, if you're programming a game, you might still do some basic OpenGL programming. If you're trying to do massive amount of data, you might actually tap into pure OpenGL programming or the shader to actually do OpenGL programming. And the web actually now has connections to your OpenGL graphics card locally. That's called WebGL. But there's languages that let you do this a little easier, to actually treat the graphics without actually having to get into the nitty-gritty of OpenGL, which you have to create buffers and windows and all sorts of complex things to actually get things running. And if you get something wrong, you'll just get black screens. So the higher level languages, SGI did Open Inventor. There's still an open source version running around. And my hope is that Open Inventor will reappear on the web soon. It's a very simple language to learn, and it does the graphics scene extremely well. There's Java 3D has been around for a while. And now the two ones that are really sprouting up are Unity and Unreal. Those are gaming engines, but because they're gaming, that means that they have really fast ways of optimizing the graphics, and talking to the graphics card, and really knowing how to treat treat graphics to be fast for shading, and even expose some of the shader language if you really want to tweak things yourself. So this is for fast real-time rendering. And there's APIs that you can tap into some of these graphics. So if you're doing C++, there's these two packages, one called Cinder and the other called Open Frameworks. You basically, after you create a wizard, you can write 2 lines of code, and it'll open a window and it'll start drawing something on the screen. It's extremely simple. It's actually based on the model that this other language called processing, which was Java-based, came up with. It was done by, I came out at MIT and Ben Fry and the whole group about, 10 years ago or 15 years ago. Within 2 lines of code, you can already have something on the screen. With 6 lines of code, you can actually have an animation that runs at 60 frames per second. You tap it into your data, and you can do something interactive extremely fast. So it's really good for prototyping, for the middle level of analysis tool that I was talking about earlier. There's been some languages that the graphics community has been trying to push that are for being efficient. There's Lua with Love and Moai as the visual interfaces. Objective-C, try to push Swift. That's the Apple stuff. And then we talk about JavaScript. So JavaScript, for the language, there is some ways to actually create graphics and plop them on the screen. And that's what we're talking about, Plotly, D3, and Vega. And I'll talk a little more about those because they're special cases. So those are things that tap into the fast renders, but the opposite would be things that actually are much lower to render, but can actually do reflections, refractions, and all sorts of interesting light mechanisms. So those would be called ray tracers. Ray tracers, things that actually do pixel by pixel. They shoot a ray and they see everything that it can collapse in the scene. And those are good for volume renderings. Lots of models of the universe can actually be done using volume rendering and ray tracers, or usually custom ray tracers. But there's fairly few ray tracers out there. The 2 most popular ones are POV Ray, which has been open source for a really long time, and then RenderMan. RenderMan is the one that actually came out of Pixar and ILM, and it used to cost about $6,000 per seat. And as of a year and a half ago, for academic usage, it's actually free. So there's some usage of actually RenderMan that's coming up. Now, modelers, so things that actually let you create geometry, create little alien-looking things, or create watertight meshes, they usually come with their own ray tracers as well. Many CAD, pretty much all CAD systems actually come with a ray tracer, or as well as connections into RenderMan and other packages on the back end. And that does include Blender and Maya, which are the most common graphics one. So these are some results from Blender. These are some biological-like looking models. This is something from POV Ray. So you can see the reflections, the refractions, the quality of it. It'll take you 5 minutes to render this image. but it'll do pretty well. This is from RenderMan, which until long ago there wasn't anything particularly interesting being rendered for scientific use in RenderMan. But now the perceptual ocean, which if you look for it, has these gorgeous images of ocean eddies and simulations of those from the Menasa group. They're pretty impressive, and they're beautiful, and they're actually using RenderMan, or the free version of RenderMan. They did it about a year and a half ago. And they use this whole Van Gogh style, so it has some very cool applications. So those are ray tracers. Yes?
The visualization, the ocean visualization, what's the technique that was used?
It's not line integral convolution. No, it's close. It's a bit of particle tracing, but it's very minimal, and it has a bit of fade off at the end. But it is kind of SEMrush. It's close to Lick, yeah. So now the last part would be graphic interfaces, and at this point, the only real one that's interesting is web-based and HTML, right? We can create all sorts of packages and front faces that have all our packages and servers things running in the back. And we can do that very easily and very quickly, and you can hire anybody to actually start programming things on the web and form-based. So that's much easier than the other packages for building user interfaces, which includes Java Swing, Qt, which is probably the most platform-independent one, or at least has compilations for all the different platforms. There's GTK, the TickleTK is still around. Python has WX and Kiwi, and they're just barely capable. Everything you can do here, you can probably do much faster and much easier with some kind of web-based interface in the front. And of course, probably the other more popular ones are anything on a phone, so either Android or Cocoa or anything, or iOS. And the last thing would be things that actually do end-to-end work for you. And that would be the world of visualization systems. So each field has its favorite package. There's TopCat, which you guys pretty much all know about. In biology, there was Modrian, which Molegro actually. Modrian's a package that was developed on top of Java, which was very strong, has some very cool brushing techniques to it. For InfoVis, the real package that is just making lots of waves, and now it's a $3 billion company, it's Tableau. So Tableau lets you do lots of import lots of data. It understands lots of databases. It lets you create interactive dashboards. It does all sorts of interesting things. But then on the SciVis side, there's actually 3 tools. And the 2 more interesting ones are actually VTK-based, which we talked a little bit a while ago. Now, the reason those 2 packages have been able to survive is because the national labs have been pumping money to Kitware, who created VTK, to actually upkeep and create these packages. Out of those, the one that I find most useful is Paraview. So Paraview lets you do some pretty gorgeous stuff pretty quick. It lets you actually, it handles, as of 5 years ago, it actually even handles large CSV files, and it lets you translate data tables into actually points in 3D space. And you can go from something simple like the Bluntfin dataset, which was one of the first simulated datasets for fluid dynamics. You can create some very cool pictures from that dataset, in minutes. It's almost like Photoshop. You just open the dataset, start applying filters, and things just show up on your screen. You can then create animations. You can rotate the camera around. You can actually do stereographic stuff, or you can even dump large resolution images. And it's called Paraview because it actually lets you open Paraview running in parallel, either running the graphics parts in parallel or even running the computation in parallel. So it actually is quite strong and lets you do some pretty cool, some pretty gorgeous stuff pretty easy. If you never got a chance to play to Paraview, try it. It actually has even some level of resolution stuff built in. It has some pretty cool stuff. And because it's been developed kind of like an open source kind of environment for national labs, it actually has full Python encodings in the back. So anything that you do can be exporting as a Python script, and then you can mess around with it. You can even connect it as a part of a batch script. So that is visualization systems. But there's something very important to talk about, is the web again. There's one package out there especially, which is called D3. D3 is just basically an accessory or a package for the web that lets you grab data and connect your data to visual elements on the screen. So if you say, okay, I'm going to create 100 spheres and have a data set that has 100 points, I'm going to connect them, and then I'm going to say, okay, every sphere needs to be in this space in 3D, and needs to have this radius and this color. And because it's web, it's really easy to create events for clicking, for sorting, for moving things around, for forms, for thresholding. So it's, a package like this, this is some self-organized map visualization that I did for a biology group here. It took me, I think 3 or 4 afternoons to create the basic version of this. So it's actually extremely easy to use. Everything on the left is just basically simple HTML, tables and forms. And if you get into the whole CSS, you can do pretty gorgeous stuff and pretty interactive. So it all comes down to how do you represent your information, what tools you have, and then going back to the original point. You have some data. The choices that you make will make this data look different. Just by choosing color, you can create things that all of a sudden are being a regular grid. Now you see, okay, there's half of them are orange, half of them are blue. If the location is different, our eyes are really good at associating things. So for most people, rather than seeing as orange and blue things, now you see, well, there's a little cluster on the left and there's a little cluster on the right. So there's no order to these things that doesn't come from just our cognitive system and the way to understanding. So through use of repetition and contrast and alignment, proximity, our eye will understand different things. And like I said before, it all comes down to this idea of read order. What is the thing that sticks out the more? How do you actually play with the variables and the data encoding channels that you have to actually represent all this information that we're showing? And there's this concept that Tufte loves talking about, which is the idea of chart junk. What is necessary in the things that you're looking at and what's not. You look at something like this, your eyes naturally want to align things. They naturally want to connect things that are the same color. If something's a little bit of color, your cognitive system doesn't know whether those things belong together or not. So really simplifying the way you present information is extremely important. When you have this is a classic, has a gazillion things that are showing that are bad uses of graphics. Everything from the font, which is a complex font with little serifs, to gradients, to a really strong grid. This is exactly the same information, but just getting rid of all the junk. The narrative that you show, the amount of information that you can ingest from this to this, can be quite different. And if you're trying to really convince somebody of somebody, or you're trying to discover things, this gives you a lot extra information that we probably don't find necessary. Even something as simple as box plots. These are good. There's nothing wrong with these. But by switching a couple of things, you go from a space where it's really about the boundaries to talking about the center point and what story that tells. So there's always a narrative to be told when it comes to these visual things, and there's always ways of cleaning up something. Again, here, gradients and lines, repetition. This is not a bad-looking plot, but cleaning things up really kind of just put things a lot simpler to understand. It can make a much better sense. So let me just jump to the last big piece of information, which is the use of color. So monochromatic color maps are extremely easy to use, and they usually show information fairly well. So here we're using just blues or just magentas. But we usually want to say that, yeah, color is a good way to bring up information. Why shouldn't we use all the color that we have? Well, for one thing, when you talk to artists, this is the color wheel that artists understand, right? Where opposites are complementary colors. They actually stand out quite in direction to each other. Where the opposite hue actually is meaningful. That's different from the color wheel that we're used to as computer scientists, where it all has to do with the way we decided to say, okay, we have red, green, and blue channels. This is the easiest way we can actually come up with these colors together. So the amount of green that's actually being shown in this color spectrum is not equivalent to this map, where we actually have just a smaller band of different colors. Here we have a really bright green that's really oversaturating the space. And that's just because of the color mapping that we use. So there was a big fight about the use of the rainbow color map. And again, that was 15, 20 years ago. Nowadays, most packages know that, yeah, the spectrum color map, the rainbow color map, not the best thing to do. And why? Well, it all has to do with our biology, right? We have cones and rods in our eyes, and as it turns out, our ability to perceive blue is not the same as our ability to perceive other colors. So blue actually comes across much darker than any of the other colors. So even just looking at a standard color wheel, and we're just going to we're going to ignore the magenta in the middle and try to make it as close to a rainbow color map, you see a luminosity ramp on the right. And you can see that the blue is actually much darker. In fact, most computers have a way to change an image to grayscale. And this is what you get. You see, well, this thing, which you would expect to be is full hue, full saturation, to have kind of the same tonality, some luminosity across. You can see that you go around the circle, there's definitely spots that are brighter and some spots that are darker. All you have to think about it a little bit is like, yeah, well, yellow is definitely brighter. And blue, yeah, I guess blue and purples are darker. So can we correct for these things? Well, even if we try to make the blue a little darker and make the red a little brighter, we end up with something like this, where if we take it to grayscale, you see that on the top there is definitely not the monotonic increase that you want for the color map. So if you want a color map that's really objective, then there's options, right? So this is the Viridi's color map that by now I think pretty much everybody's used to, because it comes standard with Python. Again, this was a big fight to actually get this incorporated. 10 years ago, most people didn't have this, but now it's pretty standard. And again, this is a cute little trick where you actually see the A and B, and even our perception of color. A and B actually are exactly the same color. They're exactly the same luminosity. But because our system tries to accommodate for what we think the scene is, well, color is just naturally a bad way to encode information, or not the best way. So we always have to be careful. Our counting system will try to accommodate. There is color maps that actually work with perception. This is called the Mansell color map. There's ways to translate that information. These are all the color maps that actually come standard with MATLAB nowadays. And if we go to grayscale, then lots of them do have that monotonic increase that we know is a little more objective. Some other ones do have some pretty strong bumps. And as long as you're designing for that, you're basically creating the equivalent of contours when you're actually mapping information. So there's actually nothing wrong with it. It's just you just need to understand and be aware of the things that you're doing. And the final little bit is continuous versus discrete. By putting things into buckets, into bins, what you actually create is you create harsher boundaries. What that means is that while you're obfuscating a little bit of the information right here, right, you do make a very clear boundary of some of the data right here. So it's much easier to pick out the kidney right here on this little mouse embryo on the right than it is on the left. Even though the left guy actually lets you, if you had a color meter, you could actually extract the original information much better. And again, for cognitive systems, it turns out that discretizing lots of information, putting it into buckets, can be quite useful. And again, that goes back to the first thing that we said towards the beginning, that categorical data maps really well to discrete color maps and to hue versus continuous data. So you can actually create sets of discrete color maps according to what you want to do, and you can just kind of increase the number of these bins and buckets that as you create. And you can actually get some pretty far with the things that you're doing. If anybody wants to talk to me, I've been doing quite a bit of work in VR lately. I've done some work with Ashish, and understanding information in VR can be quite interesting. It's tricky, and you have to know when to use VR, but it can be quite cool. I'm willing to answer any questions about interactive visualization, which I didn't cover. I basically want to just give you a good sense of what it means to actually use encoding channels, color, understanding how to be just delivered about the data visualization you want, and just kind of give you a good overview of some of the tools that are out there, including some of the tools that I think are particularly neat, including Paraview, Tableau, the Virtualytics software is kind of interesting if you want to talk to George. There's all sorts of things, and D3. So that's my time. Thank you.